Okay, here we go. So I'm gonna come back to these two questions. I'm gonna come back to these um, from the work yesterday. But the first thing I want to do is I want to talk about Q, and then we'll talk about those two questions. Okay. So I'm looking at the work that I assigned you for today. All right, and the first part is to calculate this, what we call Q. All right, and basically Q is the initial set of conditions that you're given, and you need to determine again which direction it's going to shift. It's going to shift left or is it going to shift right? Okay. Oh, and you can ignore this for the first. I forgot to erase this part for this first one. It says then find the equilibrium concentrations for this first one. You can ignore that. I meant to cross that out for all of them. Don't worry about that one. So here, we're given this reaction. At 740 degrees Celsius, AeQ equals 0.0060 for the decomposition of calcium carbonate. Find Q and predict how the reaction will proceed. If the concentration of CO2 is equal to 0.0004 molar. All right, now, first of all here, this one's a little bit of a trick question here because in the KQ statement, we don't include calcium carbonate, we don't include calcium oxide because they are solids. Okay, so really the K here, the KEQ, is equal to just the concentration of CO2. That's it. That's really what the KEQ is equal to. All right, and we're going to assume here that we have enough calcium carbonate solid, that there's just excess calcium carbonate solid there. It's probably just sitting there, and it's in a, like, we're just going to assume like it's in a container, something like this. There's some calcium carbonate in here, and then there's some CO2 in the container. And we want to know, will this CO2 turn back into calcium carbonate, or will calcium carbonate continue to decompose and form carbon dioxide, basically? That's basically what we're asking here. All right. So what we need to do is we need to look at Q and compare it to KEQ. Now, Q is the same, it's set up the same way, it's just the concentration of CO2, but we don't know if it's at equilibrium or not. Okay. So here, Q is equal to the concentration of CO2, which is just 0.0004 molar. Okay, and we know that KEQ is 0.006. So if we compare Q and KEQ, Q is smaller than KEQ. Q is 0.0004. And KEQ is 0.006. So Q is smaller than KEQ, meaning that if we were to look at it, the concentrations right now, they're not high enough in the product side, so we need more products. So it's going to shift to the right. It's going to shift that way so that we get the KEQ to be bigger. Okay, it's going to shift so that the KEQ will become bigger. All right, so we know the equilibrium is going to shift towards the products. It's kind of hard to see in that one because it's just one reactant, or one product, I should say, one reagent. Okay. Number two is a little bit better. Number two is a little bit better example here. So here we have an equilibrium constant of 5.10. That's our KEQ. Okay. If these are the original concentrations of all the reagents, which direction is this going to shift? Is it going to shift left or is it going to shift right? Is it going to move towards the products or is it going to move towards the reactants? So in order to find that, we need to find Q. And Q is equal to, again, same thing, it's just the concentration of CO2 times concentration of H2. So this is just like the KEQ statement, okay, and then CO and H2O. It's basically the Q is basically the KEQ at non-equilibrium times. So it's the products over reactants, but we don't know if it's at equilibrium or not. So that's what we're trying to find out. Okay, so the CO2 is 0.37. H2 is 0.42. CO is 0.15. And H2O is 0.25. Okay, and we do that in math there. I got to do it. I didn't do it just yet. Let's see here. .37 times 0.42 divided by 0.15 divided by 0.25. And I got 4.144. So right now, the Q is 4.144, and the KEQ is always 5.1. So the KEQ is bigger than Q. So again, this Q needs to get bigger, right? It needs to get bigger in order to equal KEQ, in order to get to the equilibrium ratio of products over reactants. So if that's the case, we need to shift towards the products to make it bigger. We need the numbers on top to get bigger. The numbers on top are products. So when you shift to the products, going to shift to the right. Does that make sense? Should we do one more? Yes, no? Yeah, try one more? Okay, let's do one more. I see some nodding of heads, so let's do one more. Okay, number 3 here. So here we have a KEQ of 0.064. This is the reaction. These are the initial concentrations. H2 is 0.45. H2O is 0.37. Okay. Oh, did I miss something here? I think we missed. Oh, no. Okay. I forgot. We don't include solids in the equilibrium expression, so we don't have to worry about those. I didn't even see the S there for a second. So Q is equal to concentration of H2O to the third over the concentration of H2 to the third. Right? Products over reactants. Again, Q is the same thing as KEQ. It's just we say Q because we don't know if that equilibrium or not. And KEQ is the equilibrium constant. So yeah. So H2O is 0.37. And then H2 is 0.45. And we get, so let me see what that is. Okay, I got 0.56. Okay, so here, this is the Q. Q is 0.56. KEQ is 0.064. Uh-oh, what happened there? Oh no. My program just knocked out on me. Come back to me. Give me 1 second. Ah, there we go. It's back. Okay. So Q is 0.56. Okay. The KEQ is 0.064. Therefore, the Q is greater than KEQ. So that means we have too much products now. The top number is too big, right? So it's got to shift towards reactant, so it's going to shift to the left. It's going to shift to the left. Okay, so Q will help you determine whether things shift left or right. Shift left or right, given initial set of conditions. Okay. All right. Next. So number 2 and 3 on that worksheet that I gave you are actually on this worksheet too. If I can find them. It's actually number 2 and 3. I think actually number 1, 2, and 3 are the same as the ones I gave you from the from that yesterday's worksheet. I probably should have held off on those. Okay, that's okay though. It is what it is. So this is actually the worksheet you're assigned today, but it's the same thing. So we're going to use these things called Rice tables to determine or figure out what the final concentrations of the reactants and products are once a reaction reaches equilibrium. So here we start, we use these things called Rice tables. It's called Rice because it's R-I-C-E. So reaction, initial, change, equilibrium. And then I have the answers down at the bottom. I added an F at the bottom, Rice if, but you don't really need to add the F at the bottom, but whatever. So here the reaction is H2 plus I2 is in equilibrium with 2HI. Okay, now the initial concentrations, we start with 0.1 of this, 0.1 of this, and none of this, which is, there's nothing of this. Okay, now because we start with only reactants, we know that the reactants are going to go to products. So the change here is going to be minus x, we don't know how much, but we know it's going to be minus x, and we know that this is going to be plus 2x. Now this is tricky. It's plus 2x because you have the coefficient 2 here, okay? So the 2 makes this 2x. All right, now my equilibrium concentrations are going to be 0.1 minus x, 0.1 minus x, and this is going to be 2x. Okay. Now this one was easy because we only started with reactants. We know which direction it's going to go. Okay, and pretty much actually all the ones that we do today, they're either going to only start with reactants or only products. So it's just going to go one way or the other. You don't actually have to find Q. Later on when we come back from break, we'll do ones where you actually have to calculate Q first and then determine which direction it's going to move, either left or right, and then do all this. Okay, so here is the equilibrium concentrations of everything. All right, and what we're going to do is we're going to plug that into our KEQ statement, our KC statement. So KC is equal to 64, and it's also equal to the concentration of HI squared over the concentration of H2 times the concentration of I2. Okay, now we're going to plug in our numbers. HI is 2x, so we have 2x quantity squared over, and then H2 is 0.1 minus x. So you're just multiplying those two things together. And for a lot of these problems initially, you're going to get basically this. You're going to have like a squared over a squared. So here you have 2x quantity squared over 0.1 minus x quantity squared. So, and that equals 64. So what we can do here is we can take the square root of both sides. We take the square root of both sides, right? Oh, I'm sorry. I'm looking at this problem all wrong. I'm doing it backwards. I'm sorry. I just caught myself. We're trying to find KC. The way I was doing it was fine for something else, but anyway, let me see here. I got to change this up. Okay, so I'm sorry. Here we have we're told that the equilibrium, the I2 concentration dropped to 0.02. Okay, so that means that these two are 0.02. They're going to both be the same, right? 0.02, 0.02. Okay, sorry, y'all still with me here? sorry, I got a little, I looked at this as if the Kc was what we knew, and we were trying to find the equilibrium concentrations, which we can do. We can do it either way. That's why I got sidetracked there. I got a little confused for a second. Okay, so we know that equilibrium, this is going to be 0.02, 0.02. So basically, we need to know what was the change then. So we need to calculate the change. What was the change? Well, 0.1 minus 0.02, we know that it went down then minus 0.08. 0.08 minus, right? Okay, so it went down 0.08. And really, I mean, we could have figured that out anyway, but this 0.1 minus 0.02 should give you this change, all right? We also know that in whatever this goes down, this is going to go up by 2. So this is 2 times 0.08. And that's adding to it. So it's going to be 0.16. Yeah. So we know this goes down to 0.02. That means it lost 0.08 molar. Both of them lose it because if one goes down, the other one goes down with the same amount. And then this one goes up by twice that change. That's why we get that 0.16. Okay, so these are the equilibrium concentrations of those. Okay, and then we just plug it into our equilibrium expression. So Kc equals the concentration of Hi to the second over concentration of H2, concentration of I2. That's equal to 0.16 squared over 0.02 squared, basically. And when you do that, uh, 0.02 to the second. We get 64. Just making sure. Okay. So that's basically I do number 2 there. And again, that was the same one from the homework yesterday, or the work yesterday. Okay, number 3. Number 3 is what I was just doing, actually. So this is really what we use rice tables for. This is the kind of problem we're going to use rice tables for, okay? This is the most useful one. So here we start with, we have the reactions. So we have N2 plus O2 yields 2NO. Okay, the initial concentration of all species in the reaction starts with 5 times 10 to the negative 4th moles of NO in a 10-liter. Sorry, we want to know the concentration of all species if the reaction starts with 5 times 10 to the negative 4th moles of NO in 10 liters. So first of all, we have to find the concentration. So we just take this moles and divide it by 10 liters. So 5 times 10 to the negative 4th moles divided by 10 liters. And we get this initial concentration is 5 times 10 to negative 5th molar. Okay, and then we start with 0 and 0. And then we know because we start with only products, we're going to shift to the left. So everything's going to shift to the left. So that means we're going to minus something here. And it's going to be minus 2x. We're going to call it 2x because it's 2. So really, you always are subtracting or adding 2 times whatever this number is, or the coefficient times that number, x. Okay, and then these will be plus x and plus x. So the equilibrium concentrations will be x here, and this is going to be 5 times 10 to the negative 5th minus 2x. That's our equilibrium concentrations. And this is where rice tables come in handy. Okay, now we write our KEQ statement, or KC statement. KC is equal to 0.2. And I'm not going to write out everything, but it's concentration of NO squared. So it's going to be 5 times 10 to the negative fifth minus 2x squared over x times x, or x squared. These are the simplest ones when you have a squared over a squared, because we can take the square root of both sides. Makes it a lot easier. So we take the square root of this side, square root of this side, and we get the square root of 0.2 equals 5 times 10 to the negative fifth minus 2x over x. And then basically from here, we're just doing algebra. We're going to be doing some algebra to find x. We're going to be solving for x. So we get x on the square root of 0.2 equals 5 times 10 to the negative fifth minus 2x. We add 2x, add 2x. That cancels that. So 5 times 10 to the negative fifth equals 2x plus x square root of 0.2. Okay, and then at this point, it's really now I just do 2 plus square root of 0.2 times x. This whole quantity, I should say, actually, equals 5 times 10 to the negative fifth. And then divide both sides by 2 plus square root of 0.2 x, and then leave x, then x is by itself. So it's 5 times 10 to the negative fifth divided by 2 plus square root of 0.2. So you put this in your calculator, you're going to find that it equals about 2.05 times 10 to the negative fifth. And then when you do that times 2 and subtract it from 5 times 10 to the negative fifth, you get 9 times 10 to the negative sixth. Those are your equilibrium concentrations for that. Does that kind of make sense to everybody? Sort of, kind of, really? Okay, let's look at another problem. Like I said, I gave you a lot of these problems, so it's really doesn't matter if I go over a bunch of these. Okay, number 4 here, the reaction CO, H2O, CO2, and H2. The initial concentrations, so if 0.1 moles of CO and H2O, so it's 0.1, 0.1. It's in 1 liter, so we don't need to divide it. It's just 0.1, 0.1. And then we know that these are 0 to start out with, so we know it's going to shift to the product side. So this is going to be minus x, plus x, plus x. Okay, so equilibrium concentration is 0.1 minus x, 0.1 minus x, and this is x and x. So again, using our KEQ statement, our KC statement, KC equals 4.06. That's equal to products, or x squared, because x times x, over reactants, which is 0.1 minus x quantity squared. So these ones are pretty simple. We're just going to be taking the square root. You get the square root of 4.06 equals x over 0.1 minus x. And again, just solving for x. Okay, so cross multiplying, square root of 4.06 times 0.1 minus square root of 4.06 times x equals x. Add this to both sides. You get the picture, yeah? That's just all algebra there. I'm not going to waste any more time with that algebra there. In the end, you get these. You're going to get x equals 0.0668. And then when you subtract that from 0.1, you get 0.332. Okay. So that's really simple. When you have a squared over a squared, you can take the square root of both sides. Okay, that will be that for that one. Number 5 is a lot like number 2 that we did, where you have equilibrium you have initial concentrations and an equilibrium concentration. So you have to figure out what the change is in it and then plug that all into a Kc expression. So number 5 is a lot like number 2. This one, number 6, is different. So let's do number 6 together. So here we have a 5-liter reaction vessel. There's this much of the initial right here. So this is 0.03 over 5 would be the initial concentration. Oh, you know what? Nope, never mind. This one's just like number 2 as well. Just you have to figure out these concentrations because it's in a 5-liter container, but it's just like number 2. So if you want to write that down, just like number 2, just make sure you find the concentrations rather than just don't use the 0.03 moles and the 0.001 moles. Find those concentrations rather. Okay, but that's just like number 2. Let's see what else. My computer's running slow. Hope it doesn't kick me off again. Number 7 is just like number 3 and 4 and 5 that we've been doing. Okay. Let's see here. I think number 8 is very similar to that. Number 9 is, I think, the hard one. Yeah, this is the hard one. So and this is kind of an introduction to what we're going to do next time. If you get a reaction like this where you're not going to be able to square root the reaction, you're going to have to use one of 2 methods. The first method is to actually calculate using the quadratic formula. And then the other method is to use what we call the 5% rule. I don't want to get into the 5% rule today. We're not going to talk about the 5% rule today. But I'll run through number 9 here for you guys, and then I'll show you how to set up the quadratic. I'm not going to do the whole quadratic, but here we have, so here's the reaction PCl5. And then it really should be this is in equilibrium with, and I fixed this on your sheet. I forgot to download the actual correct one, but PCl3. There are some typos here. I fixed them, the ones you got. Cl2, sorry. Okay, so the initial concentrations, it's 0.2 moles of phosphorus pentachloride in 2 liters. So it's really 0.1 molar. Okay. And we want to know what is the new concentrate, what are these concentrations? What are the new concentrations after everything's done? So this is minus x plus x plus x. So these are both going to be x, and this is going to be minus x. So when we set up our KEQ statement, KEQ equals 0.6, and that's equal to the products, x squared, over the reactants, which is 0.1 minus x. Okay, and you'll see that now we can't do that square root method here. We can't take the square root of both sides. It doesn't work. And that's going to happen a lot of times. That's going to happen a lot of times. Now, typically, if this KEQ is really, really small, we can disregard this x. We could just say, okay, the x is going to be so small, it's not really going to make a difference in this overall concentration, and we can ignore the x, and we just solve for x squared. Okay. But in this case, the KEQ is actually really large. Any KEQ that's 10 to the -3 or bigger, so like 10 to the -2, 10 to the -1, or any whole number, that's a big KEQ. Most KEQs are pretty small, like 10 to the -5th, 10 to the -10th, you know. And those ones you can use this 5% rule, but we can't use it here. Okay. What instead we have to do is we have to multiply this out. So we multiply and set them equal to each other. So 0.06 minus 0.1x equals x squared. And then we make everything equal to 0. So we bring it all over to this side. So we get x squared plus 0.1x minus 0.06. Okay. And then now we have a quadratic equation, and we can use the quadratic formula to solve for x. Okay, so a here is 1, b is 0.1, and c is negative 0.06. Oh, it just kicked me out of there again. Great. But anyway. So you have to use the quadratic equation for that one. Okay. Most of the other problems you need to use the quadratic equation. If we look at let me just open up this, if it will let me. So I actually gave you all the worked out answers here for them. But that's the only one you actually have to use the quadratic equation for. All the other ones you can use that square root method, or it's actually looking for the KC in the end. All right, and this is not working. My computer is just running really slow. So let me just stop there because I think my computer might kick me off again.